everyone. I welcome you again to the next class of econometric methods. I am Dr. Muhammad Imdadul Haq, an associate professor in the Department of Economics, AMU. Our topic of discussion today is a phenomenon which is associated with multiple regression. In our previous class, we have been discussing about multiple regression. So let us take a situation that you have an equation, and this happened also on the day when we were doing regression by using the Excel sheet. We were estimating the relationship between quantity demanded, price and income. We took some hypothetical values, but when the estimated result showed that, or say we have a situation wherein quantity demanded is equal to alpha plus beta price plus beta 1 income. Now, you have the data was given to the software and the software gave the result. The sign of the coefficient is +1. So, can price have a positive relationship? Except for some extreme circumstances. Normally, the theoretical point of view, quantity demanded has a negative relationship. But what's happening over here? That is, the sign of beta 1 is turning to be positive. In the last class, when we were doing a numerical example, we were solving it through the help of the solved example was presented. We found that the variable price, it was not significant. Obviously, quantity demanded and price, they have a very significant relationship. But what happens is, if something which should be significant in a significant variable, it's a very established fact that when there is a significant relationship between price and quantity demanded. But when this relationship is not significant, it is some problem is there. Or you can say the sign, we all know that for a normal good, when price increases, quantity demanded decreases, so there is an inverse relationship. We all know that. But our beta 1 or the coefficient of price is having a positive sign. If things like these happen, then we can say that there is some issue. So, an independent variable known to be an important predictor ends up having a regression coefficient that is not significant, or a regression coefficient that should have a positive sign, it turns out to be negative, and something which should have a negative sign like price, it turns out to be positive. Also, see, if you have taken, say, if you have just taken a relationship like this, quantity demanded is equal to alpha plus beta 1 p. See, r square is equal to, we take an hypothetical value 0.60. Now, quantity demanded is equal to, I add one variable, beta 1 price plus beta 2 income. Okay. This should be like when we add one more variable, now it is increasing. It's a normal thing. But suppose there is such a case that in this case r square was equal to 0.60, and in this case r square, it becomes only 0.61, or r square becomes 0.99. Now, this is not a concrete measure, but what we are saying that when we add or remove one variable, obviously that variable with an important variable, there is a drastic change in R square, or there is a drastic change in these coefficients, this also is an indicator that something is problematic, and this phenomenon is what we call to as multicollinearity. So multicollinearity is a phenomenon which refers to the fact, or which refers to the situation where the independent variables are correlated. It is a term used when the relationship we have more than one independent variable, obviously. This term was coined by Ragnar Frisch. It indicates the presence of perfect or exact relationship among some or all the explanatory variables. It implies to linear relationship only. We will see that, and it is a sample phenomenon and not a population problem. Also, it is a matter of degree and not of kind. We will be going on. So, what happens if many a times, if you just ignore this issue of multicollinearity, what happens? R square will be high, but individual coefficient will have high standard errors. So what is the meaning of an individual coefficient having high standard error is T is equal to beta by SB. This becomes very high, this becomes very big. So ultimately what will be the case when this becomes very big? Our T stat, it becomes very small. When our T stat becomes very small, it will be falling in this region, and this region beta is not significant. So in case of multicollinearity, we find that our R square is very well, and it is our R square is significant and it is quite large, but the individual coefficients of the individual parameters, they are not significant. So this is one problem. The second is it becomes very sensitive to the small changes in the specification, as we have seen in the when we were discussing over here. There was a very huge, there is normal change. It says 0.65, it's a normal change. But the moment we add one variable and this changes drastically, if you reduce, this changes drastically, then it indicates that there is some problem. So similar can be also interpreted in terms of confidence interval. So the confidence interval for the parameters will be very wide, because obviously your standard error beta is increasing, and the significance test, it will be giving you inappropriate conclusions. So this problem is essentially a sample phenomenon. Why we refer to it as a sample phenomenon? In the sense that even if the explanatory variables are not linearly related to the population, they may be related in the sample which you have selected and on which you are working to get the estimate. So when we are postulating the population regression function, we believe that each and every explanatory variable has a separate influence on the dependent variable. But it may happen that in any given sample that is used to test the population regression function, some of or all of the explanatory variables are so highly correlated that we cannot isolate their individual influence on the dependent variable. Simply we can say that the sample regression function does not stand the basic assumption of independency among the explanatory variables that are included in the model. So first thing what we have seen, it's a sample phenomenon. Next, it is a means a matter of degree, not of kind. It is a question of degree, not kind. That is, it is not a matter of concern of whether the correlation between the explanatory variables included in the model is positive or negative. We are not concerned with that. But the main concern is to study the extent of degree of correlation among the explanatory variables. Again, it is, we are referring here to the linear relationships only. Like, see, we have taken a function, or we can just take, suppose, up till here, a quadratic function, where here x, we have the first variable x, and that is with raised to the power 1, and next time we are taking x raised to the power 2, or we take a cubic function like this, where we have incorporated a term x raised to the power 3. Herein, see, herein we are not considering the case, because this is the same variable. Here, multicollinearity refers to linear relationship among explanatory variables. It excludes nonlinear relationship among the explanatory variables like this. This nonlinear model does not violate the assumption. But if we have a case like this, beta naught plus beta 1 x xi plus beta 2, then we have z square, then it becomes a different thing. These two variables are not the same. But when we are taking the same variable and we are incorporating a quadratic or a cubic term, it's not an issue. Why does it rise? Why there is a problem of multicollinearity? See, the reason is there is a tendency of economic variables to move together. Like you say, you take an example, you GDP, and if you assume it to be a function of this primary sector, secondary sector, and tertiary sector. Although this is an this here, these two things will increase over the time. Oh, there will be, if there are structural changes, they will show different type of movements. But what I am saying that over the time, these things, they tend to move together. So there is bound to be some sort of relationship between these two. And see, we will see in the coming slide, in our coming discussions, we will listen that many a times researchers tend to ignore this problem. They ignore it up to a certain extent, that if their variables significance are not impacted as such, but means they tend to sometimes overlook this, because economic variables, they are supposed to move together, they will move together with time. Again, see, use of lagged variables of some explanatory variables as separate independent factors. Means you are taking a lagged variable. So obviously a lagged variable and its real original variable, there will be some sort of relationship between these. So with normal time series data also, time series data, these type of problems, they are somehow going to happen. So now the question is, what leads further? Then you can say that the data collection method. So sometimes it may happen that the data is collected over a range of explanatory variables, where the variables are linearly dependent. For example, sampling is done only over the limited range of values taken by the explanatory variable in the population, and say for it is mere chance that in that particular range there was an association between the independent variables. Then model and the population constraint, you can say there may be some constraints on the model of the or the population from which the sample is drawn. The sample may be drawn from that part of the population having a linear relationship among the explanatory variables. So sampling and the model that has been constituted. Now identities, existence of identities. See, there may be some relationship among the variables which may be due to the definition of the variable or any identity relationship among them. Like take an example, GDP is equal to primary sector plus secondary sector plus tertiary sector. This is an identity. There will be a relationship between the explanatory variables. Such a relationship will not change even if you increase the sample size. Increasing the sample size is one of the solution to the problem of multicollinearity. We will see that. An overdetermined model. See, sometimes to make the model more realistic, a large number of explanatory variables are included in the model. Consequently, the number of observations becomes smaller than the number of explanatory variables. That is, it becomes small as compared to k. Such a situation can also arise in, say, medical research, where there may be very small number of patients about whom information is to be collected on a large number of variables. But in many, and this can be very easily controlled in economic data, because we can have a large number of data. We can have over the years a long series of data. But an overdetermined model means where you have taken lot number of explanatory variables. It also leads to it also leads to multicollinearity. Then the lagged explanatory variables, we have referred it to earlier also. So that is, multicollinearity may arise due to the use of lagged explanatory variables in the regression model. Say for example, to estimate consumption expenditure, past income may be included as a separate explanatory variable along with the present income. And so, in which it is very natural to observe the correlation between past income and present income. So, these type of things also leads to multicollinearity. Now we move to the next section, that okay, there is multicollinearity, then how to detect it. We have discussed before also. R square is significant, R square is high, but the t values, or you can say the individual coefficients of the individual variables, independent variables, they are not significant. A classic symptom of, say, multicollinearity, you can say the R square is high, say between 8 or 0.9, as in the question which we had solved a question on multiple regression. We find that the R square was 0.99. Then the F test will show that it is significant, rejects the null hypothesis that the partial slope coefficient are simultaneously equal to 0. The F test will show that the R square is significant. But when we investigate the individual t test, like we had done the t test for one of them, that is the first, we had done it for only the first variable, then we had seen that it was not significant. So they show that only one or very few of the partial slope coefficient are statistically different from 0. And if we find such a thing, that is R square is high and significant, but the individual variables are not significant, so it indicates at the presence of the problem of multicollinearity. Another way to have a lookout, and this is a very crude way, but it's so we check the correlation coefficient among the independent variables. We simply calculate the Karl-Pearson correlation coefficient of the independent variables. This is basically a rule of thumb. If the correlation coefficient between two explanatory variables is high, say more than 0.8, then multiple collinearity, then we can say that there will be a multicollinearity issue. Now, but this is not a crude method. This is just a rule. There is just a rule of thumb. This is sufficient in case of two explanatory variables, but in case of, say, models involving many explanatory variables, more than 3, 4, the zero order correlation coefficient will not provide an perfect guide to indicate the presence of multicollinearity. But as a prima facie, if the correlation coefficients are very high among the independent variables, we can expect that we will be facing the issue of multicollinearity. Another way out, another thing is variance inflation factor. Now, what we do, we regress one of the independent variable on the other independent variables. We calculate R square. Now, then we have a formula of this variance inflation factor, that is 1 upon 1 minus R square. Now, we find, so again there is no hard and fast rule that what will be the criteria, but the thing is, if it is high, if the VIF is high, there will be a problem of multicollinearity, and normally researchers go by, there is again a rule of thumb that if the value of VIF is more than 10, then there is a problem of multicollinearity. But here how we are calculating the R square? We are calculating the R square by regressing one independent variable on the other independent variables. Nothing is being done with the dependent variable. The next method we can say is again a stepwise regression, like what we are seeing here, that we are estimating a model where first we take one independent variable x1, next time we incorporate this was the first, only we have taken x1, next time we have taken x1 plus x2, next time we have again increased one more. See, in such a case, if multicollinearity is absent, estimated parameters should not change from one step to other, and there may be a small change in the standard error, but not a very large one. Means, say, just hypothetically here b1 is equal to 0.9 0.8, here okay, it will be also 0.8 not 9, or it will not be the case that, and moment we that it will not be the case that this becomes 6.5. The moment this thing is happening, we can understand that because of the incorporation of this x3, something has happened which has highly increased the value of this b1. That is, if multicollinearity say b1, also the same thing, not only because of the value of the parameter, also about the significance. Here b1 is significant, here say b1 is significant, but upon incorporation of this becomes, b1 becomes not significant. It means this insertion of this x3 is creating an issue. So again, R square also we have to check, gives an indication of the multicollinearity. Say when we move from here, R square was equal to, say, R square was equal to 0.4, here R square is equal to 0.5, and the moment this is incorporated, R square is equal to 0.99. So R square also gives an indication of multicollinearity. And say when we move from the second step to the third step, we find, or like another case can be, it is say 0.6, this is 0.7, and when we incorporate this, it becomes 0.71. There is no such change. This change was okay, it was increasing by 10%, but with herein there is increasing by only 1%. So if things like these are happening, then stepwise regression is a very good tool to understand this. Now there can be two reasons why R square is not increasing, like why it was happening over here. It is not increasing, it was 0.7, again it is just 0.71, where in the earlier case it has increased from 0.6 to 0.7. It could be that the variable itself is irrelevant. The variable x3 is of no use, it is not related to the independent variable, or there is a large change in the standard error of B1 and B2 because of the incorporation of this. Now, the moment the standard error, as I have told earlier also, see, you have this T, it is B by SB. The moment this become big, this entire thing becomes small. The moment it becomes small, it will fall in this region. If it is falling in this region, your variable is not significant. Now, there is another test which we will be looking at, and that is the Farag-Glauber test. See, what we are basically doing is here is we are calculating first we are just in taking the independent variables. X1 is an independent variable and the other are x2, x3. We calculate r square. Then next time we take x2 as the one of the independent variables as the dependent variables, and then we calculate x1, x2, x3. Then we can calculate the F ratio. So here basically regression is performed only with the independent variables. We do F test. If this F test is not significant, we can say that the overall the model is insignificant. Say through F test we found that x1 is significant and all other x, the other remaining x are insignificant. It means there is a strong relationship between x1 and other independent variables, or in other words, it is multicollinearity. So your case is, if suppose x1 and x2 are significant, it means x1 and x2 are having a linear combination of the remaining variables. Here the F ratio is calculated using the formula, and the null hypothesis is no multicollinearity, and the alternate hypothesis is there is multicollinearity if my F calculated value is more than the F if more than the F table value, we reject the null hypothesis. Normally F tables they are just on the right hand right tail test. So if my value is falling over here, then this is H naught is rejected, H1 is accepted, and for the entire region this H naught is accepted. H naught is accepted means H naught is accepted means no multicollinearity, means there is the problem, it is a problem, and if it is falling over here we can say it is no problem. So we will stop over here for today. What we have done basically, we have discussed the problem of multicollinearity, why multicollinearity is happening and how to know that there is multicollinearity, what are the issues which happen because of multicollinearity. In our upcoming classes we will go for the solution of multicollinearity. Thank you.